Oh, so I'm going to go over this dome thing that Gary referred to a while ago. I'd heard of it before, but I had never really read it that closely. So it's by John Norton from the Department of History and Philosophy of Science at the University of Pittsburgh. It's called The Dome, a simple violation of determinism in Newtonian mechanics. And I thought, now I don't endorse this, because I don't believe Newtonian physics applies. So this is just a mathematical oddity, like a kind of a mathematical puzzle. You go, oh, that's interesting. So I thought I would explain what, I took the time to figure out what they were saying in here in terms I could understand, and I thought I would explain what's going on here. Now, one thing is that in Menham we'll find this easy to reject still. This is good, too, because, as I said, I don't accept this as a physical statement. This is a little mathematical puzzle. And the reason is that Newtonian mechanics has phantasmagorical aspects that are employed in this. It's the weird aspects of Newtonian mechanics that are the problem. So maybe we should reject that and go back even further, but or just go on to quantum mechanics, either way. But I'm getting ahead of myself. Anyway, so for example, there's Galilean relativity in Newtonian mechanics, which is velocity relativity. So if you're in a spaceship and there's a spaceship coming at you at 2,000 miles an hour, in that spaceship, it not only looks like you're going at them 2,000 miles an hour, you really are. It's indistinguishable. Which of you is moving towards the other is just a matter of point of view, of position, of reference frame. Okay, that's the kind of relativity that Newtonian physics was dealing with. Okay. Now, another kind of relativity, or at least a related thing, is the idea of time reversibility. Okay, the fact that it looks like things are going forward, that's relative to us experiencing time in that direction. In Newtonian interactions, things are reversible, and this follows from various things. Okay, but well, just one philosophical description of it is, if you have things deterministically going 1, 2, 3 in this direction, you can always go 3, 2, 1 backwards. You have to be able to, so even though you don't see time go backwards and you're not saying time goes backwards, mathematically, time can go forward and backwards, okay, for Newtonian mechanics and all its elastic things to work. So, for example, one example is this. If you bounce a rubber ball and you know how you bounce it, and if it's spinning, it bounces and it goes back and forth, right? It goes boom, 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 boom. It bounces like that. And if it's perfectly elastic with no friction, it would do it at the same height. So if you threw it this way and it's bouncing, it kind of goes like this. It bounces back, makes a little hop back and then forward, and it keeps going. And with time reversibility, if you see a diagram of this, it's a diagram of time going in either direction. Either the ball on this side with its initial motion bouncing that way, or it starts on this side and goes the other way. Time's supposed to be reversible. And that's an issue in this. But also there's just the reason time is supposed to be reversible, which is the mathematical statement. Okay, now if you have F equals ma, to apply this to this situation and to see what its velocity is at this 0 point, you have to use calculus. Newton invented calculus. And this is how an introduction of a little lateral component, which starts this thing in motion, comes in. They don't go into this in the paper, but this is where that comes in. If you're wondering, like, how could it ever start moving? It's because in calculus, you can't cut a path down into points. You have to cut it down into little infinitesimal sections. These little infinitesimal sections are the path cut in an infinite number of parts. So they're basically like the width of a point, but they have a width. Okay, there's an infinite number of them fit in, but they have a little line segment, so they touch the one next to it. And this is really important. This is how Zeno's paradox is solved, and if you don't do calculus, you can't do Newtonian physics, which again is why Newton invented it, or was one of the inventors. He at least invented, I think, the one he used. Reversion. So when you apply F equals ma in the Newtonian physics to this and try to figure out, well, what's its velocity, and velocity means the change in distance over the change in time, right? So, and you have a little infinitesimal bit of time and a little infinitesimal bit of distance that's sort of assumed in like that. Well, one solution is it sits there, but the other solution is that it's in motion. Okay, now you can imagine how it's in motion through the reversibility, right? Since you can take the thing, always reverse the physics, right? Imagine one way that it's at rest is if you rolled it up the hill. If you rolled up the hill and you did it too hard, it goes over, and not hard enough, it rolls back down. But if you do it just right, it comes to rest at the top of the hill. Well, with the shape of this dome, it takes an infinite amount of time for it to actually come to rest. It slows down so much at the top because of the shape as allows this kind of slowdown. It takes an infinite amount of time to get to the top. But this is reversible. So that means one of the solutions of it being at the top is it's in the process of this infinite motion that it would take forever to do. So this is one of the ways that the thing can be at the top. And the introduction of the little component is because in calculus you have to use these infinitesimals. And so the equation introduces a little tiny bit of non-zero radial distance from zero and time distance from zero. And so some of the solutions of the mathematics that in a normal physics, Newtonian physics problem, you calculate all the solutions, not just, oh, x equals 0, you know, those can be trivial solutions. But you also get these other dynamic solutions, and this one has a dynamic solution, and it shouldn't. Or, you know, is 0 and it's set at the top, no friction, no forces, it should stay there forever. But this equation for this shaped dome has a solution where the thing is in motion. So now this is not about something that happens. This does not mean this happens in real life at all. You know why? Because Newtonian physics doesn't apply. So, yeah, don't worry about it.